In this section, we will build upon the static analysis by creating a rigid body motion study to understand the kinematics of the front suspension system in further detail. Starting with an assembly model, we can focus in on the front right corner of the vehicle and hide the mirrored components. We'll section the model using the front and right planes to make it easier to see the components. Taking a closer look at the suspension assembly, we see that the double wishbone arms in blue are connected to the chassis. Mounting tabs have been included to mount the orange bell crank rocker to the wishbones and shock absorber. Wishbone mounting points have been represented as simplified ball and socket joints for the analysis to allow for a full range of motion. The physical shock absorber spring has been excluded from the assembly, as this can be represented as a virtual simulation element using the simple spring equation, but can also consider fluid damping, thus negating the need to model the geometry. We can also see the purple rocker linkage if we rotate around the model, and the wheel assembly itself. Hiding the tyre and wheel, we see a simplified body representing the design envelope for the upright knuckle, shown in yellow. The brake caliper and hub axles are mounted to this body, which will be optimized in the next section. Ball joint connections are also modelled here to streamline the motion study setup. We'll unhide the component we hid earlier by using a handy little button on the assembly toolbar, and this completes the geometry review. We can test wheel clearances and suspension travel by moving the wheel to ensure all components are mated correctly. These mates will automatically be converted to motion study joints, avoiding tedious manual setup. To create a motion analysis, navigate to the Assembly tab and insert a new motion study. Ensure the motion add-in is enabled first if the options are not visible. All motion study tabs are shown at the bottom of the viewport, and clicking on a study name will split the pane and show a custom motion-specific feature tree. Be sure to change the study type from animation to motion analysis for a full feature set. This particular study has a number of pre-applied conditions which are listed. We can calculate the response using the toolbar option on the left and add additional simulation elements and conditions by working from left to right. Options to add motors and actuators, springs, dampers, forces, contact and body forces are available. We'll step through the setup. Gravity is applied to the global Y direction, but this could be modified and flipped to simulate a constant and uniform acceleration load. A virtual spring connector has been created with a linear spring stiffness and two load-bearing faces selected. Damping can also be turned on here, but we have created an explicit damper between the same two faces with a damping coefficient to control this independently. Solid body contact between the wishbone and the upright has been set to steel dry, and this is true for both the upper and lower wishbones. We can extract the contact reaction forces correctly using this method, and these are listed in the motion tree. A vertical force was added to apply loading on the wheel to simulate a bump impact. A custom driving function of force versus time was used, and the data has been imported from an Excel sheet. In this particular instance, the acceleration data was obtained by mounting a mobile phone to the engine bay of a vehicle near the shock top mounts and capturing acceleration data using a data logging app. The acceleration in the Z direction from the app corresponded to the vertical Y acceleration of the chassis. This was imported directly into Excel and rearranged by dividing the acceleration by the mass acting over 1/4 of the vehicle to give an approximate force acting at the wheel. Notably, the vehicle the data was extracted from was much larger than the Formula Student chassis, but the analysis methodology is still the same. A small subsection of the data has been extracted to show the vibration loading for 0.5 seconds. We will use this data in the motion study by importing the raw data from a .csv file. The first column represents the time in seconds and the second column represents the force experienced in newtons. This data is imported into the force function builder and we can calculate the motion. Notice how the wheel responds to the dynamic input. We can scroll down to the results folder where results will be stored. Clicking the XY plot, we can extract the wheel's linear displacement in the Y direction over the loading time and choose to show a vector arrow graphic in the viewport. We are presented with a plot of the linear displacement over time and can play this back. Ignore the displacement scaling as the input data was obtained from a much larger vehicle. Gravity is not enabled and not all materials are applied to components. Navigating back to the results folder, a previously created reaction force graph shows the forces experienced at the wheel knuckle upright, which will be used in the next phase, and the vector on screen shows the force loading graphically. Other plots that are available include energy, pitch, yaw and roll graphs, angular accelerations and much more. The motion study properties control many of the solver settings needed for robust motion simulation and include the number of frames per second for smooth animations. In this case, 400 frames over 0.5 seconds equates to 200 frames per second and the number of calculation points. Precise contact between pointy geometry and complex components can be used when the contact resolution slider cannot reach an adequate solution. More advanced options control the solver integration type, with the W-stiff solver being better suited for reducing errors, improving accuracy, and updating solver constants at each step size, which can be modified. We can now take the forces we obtained and import them into the next phase.